Hi, welcome to Mean 221. Today we are going to talk about why we want to calculate components of loads. And by loads I mean both moments as well as forces and how they are related to failure. Okay, so that's our task for today. So what I would like you to do is take something that you want to break. Something like this crayon, okay? And I want you to break it. Okay, so pause, break this thing and come back. Did you pause? Did you break it? Good. So did you see that what I would do is I would break it like that, right? Typically, you wouldn't take this and try to break it like pulling it. Okay. There's another way you could break something like this. So let me show you in a second as soon as I find. There you go. Another way to break it is to actually twist it. And it's quite hard, but if you correctly twist it, you could break it. Right? Another way to break it is if it is really short thing, you're not going to bend it. You're probably going to try and slide it. But even here I bent it. The point is the following. If you want to break something, you want to actually bend it. Bending is the most likely way of breaking something. If you cannot bend it, then probably the next most likely way of breaking is by twisting. If you cannot do that, then the most likely way of breaking is by sliding. And then the last one would be actually by pulling. Breaking something by pulling on it is extremely hard unless it's like a soft material like a polymer or something. Typical materials are very hard to break by pulling. You can break it by pushing, and I will show you how that would work. But bottom line, those are the things that matter, okay? So let's go see if we can change this. Yeah, there you go. Okay, so today we are going to learn about parallel and perpendicular components of loads, because we want to find out what component of load causes breakage. Okay, so we want to be able to say, if I give you a shaft or something like that, you want to be able to say how much force is acting this way and how much force is acting that way, because then you can figure out which forces are going to cause failure. Same way, if I grab it and I try to apply a moment to it, I want to find out how much moment is for twisting, how much moment is for bending. Okay, twist, and for that the moment has to be axial. Bend, and for that the moment has to be perpendicular. Right? Bend, twist. Okay, so those are the things we are very much interested in. So we talked about the technological relevance, the high level learning objective, the high level thinking process is that you want to find the line vector, the line along which you want to find the component. Find the component. If you want to find perpendicular things, don't try to find another line vector. Just subtract the parallel component from the total. You will get the perpendicular. This requires some calculation and some knowledge of vectors. We're going to see an example and other things. So when we get close to that, you will see how we work. Okay. So let's go. So I showed you all these different ways in which you can bend something, but I'm going to go through this pretty fast. So you can see there's the bending part, there's the sliding part, that's shear. So that's bending, that's twisting, that's shearing, like that. And then I'm trying to squeeze it. If you squeeze it, it will bend, it will actually buckle. So that's why squeezing is dangerous. Can you see that? And then lastly, if you try to pull it, it's very difficult to fail. So I want you to understand that these are the four mechanisms where something can fail. Okay? And the order of damage is the following. Bending is the worst. Twisting is next. Push and shear are similar. So sometimes things will fail by shear, sometimes things will fail by push. The last one, the safest way to apply some load to something is pulling. Now this varies, but this is generally the case. Okay? For a beam or a frame, you know what a beam means, right? Bar. Frame means collection of bars joined together. So for a beam or a frame, the force component that's perpendicular to the axis is really critical, because that's what will cause most of the failures. Right? For two contacting surfaces, sliding forces like this are the worst. So if it is a long thin beam, then it is perpendicular forces. So if it's a long thin beam like this, it's the force this way. If it is two contacting surfaces, then it's sliding. Okay, those are the typically most dangerous things you can do. I don't know how it shifted down, but oops. Okay, so now if you look at forces perpendicular, what it will do is it will actually cause this whole thing to break. This is one of the oldest problems that was considered. It was considered by Galileo in 1500s. This picture is actually originally reproduced from Galileo's work, and it is what happens to a beam when you apply a force perpendicular to it. You can see there's the force that's perpendicular, that's the force that's perpendicular, there's the beam, and he realized that something bad will happen here. A bridge shear shows you what kind of damage can happen on a large scale. Shear forces, I think you can see what has happened to this bolt. Can you see that? It's completely sheared off, and that's a very serious problem. And here is what happens if you have a bunch of bolts. You can see that perpendicular to the bolt, the load is perpendicular to the bolt, and that's the real cause for failure. Okay, and here is twisting failure. So there's don't ask how that thing got twisted so badly, but it is twisted. That's what happens if you take a twisting to a brittle material, and you can see the red regions are the ones that are likely to fail. That's a twisted bar. Okay, this is component of the moment parallel to the axis. That's called twisting. Okay, this is bending. I told you this is the worst, and you can see how it breaks. You can see gradually the failure either goes that way or kind of it delaminates, it will separate out. That's what will probably happen to wood when you do this. Okay, so you got a general idea, right? Now we come to the main task, which is if you want to figure out how things fail, you want to be able to find the components that are either perpendicular, that are either parallel or perpendicular to an axis. And when I say load, it could mean force or moment. Both of them would be considered. Okay, so let's look at an example problem. Here's a shaft. Okay, it starts out at point A, whose location is given by coordinate 071, and it's in meters. So point B is given by coordinates 913 is in meters, and the torque on it, the total moment on it, is given as 1025 kilonewton meters. So it's a vector. Moment is a vector. Question is how much twisting, that is parallel component, how much bending is what we are trying to calculate. So the trick is find this first and then find this by subtraction. We are not going to do two dot products, we are going to do only one to find the parallel component. So start, first find the line vector. This is LAB, which is B minus A, which turns out to be, if you do that, it will turn out to be 9 minus 6 minus 1. Okay, then find its magnitude. Square root of 9 squared plus 6 squared plus 1 squared, which turns out to be 10.86. Then find the unit vector. This is the vector of unit length that goes this way. Is LAB divided by L, which turns out to be 0.829 minus 0.552 minus 0.092, something like that. Okay, and this is dimensionless because these two have equal dimensions. Okay, now you can find parallel component equals F dotted with, or in this case M dotted with EAB, which turns out to be pretty straightforward. It is, look, M is here, EAB is here, so dot these two things, so it's 10 times 0.829 minus 2 times 0.552 minus 5 times 0.092, which turns out to be 6.72 kilonewton meters. That's the unit, Newton meter or kilonewton meter. So this is the parallel component. Now I want to find how to find perpendicular. Idea is to notice that this vector is the parallel component, its length is 6.72. I know this length, which is the square root of 10 squared plus 2 squared plus 5 squared. So perpendicular component equals, by using Pythagoras theorem, this will be equal to square root of 10 squared plus 2 squared plus 5 squared minus 6.72 squared. Like that. This is basically Pythagoras. And you will get the answer to be 9.15 kilonewton meters. You can see that bending is worse than torsion or twisting. So it's likely to fail by bending. Without knowing anything else, you can say, look, it has a higher bending perpendicular moment than parallel moment. So higher moment, this is likely to be cause of failure. Of course, it depends upon the material, but preliminary, that's what you can say. You understood this process, right? Very good. We'll do one more problem for a different one and we'll see what happens. Now, I don't have a line, I have a surface on which I am exerting some force. Minus 10, 4, 5 kilonewtons, and I have given 3 points A, B, D and C. And the question is, how much pulling, which is perpendicular, and sliding, which is parallel. This is actually something that's tricky because notice that I have two directions which are parallel and they are not perpendicular to each other. So this angle is not 90 degrees. So what happens is, it's not a simple thing to find if you have surfaces. You cannot find parallel forces so easily if you have surfaces. But the main thing to notice is that every surface has a unique normal direction, which means it has a unique direction that goes like that. How do you find this? This normal direction is given by AB cross AC divided by magnitude of AB cross AC. Cross product, not multiplication. Okay, and this thing means magnitude. That's what you have to do. So once I know this, I can find the perpendicular component. Perpendicular component is F dot N. Parallel component is by Pythagoras theorem. That's the trick. Okay, so let's see. So now I'm going to do AB equals, let's see, 1 minus 2 minus 3, sorry, 1 minus 2, 3. AC equals 7, 8 minus 3. So AB cross AC. You know how to do cross product. I'm not going to waste your time showing you how to do all of that. Minus 18, 24, 22. And this is meter squared. Okay. So E perpendicular is this thing divided by square root of 18 squared plus 24 squared plus 22 squared, which turns out to be minus 0.48, 0.645 and 0.591. Now I can find F perpendicular equals F dot E perpendicular. I'm not going to waste your time to do dot products and all of that. You should know how to do this. This is 10.36 kilonewtons. Here is F. Take that, plug it in here. So now F parallel equals square root of 10 squared, because if I break it down like this, if I break it down like that, perpendicular direction, I know this angle is 90 degrees. So I know this, this angle is 90 degrees. So I know that. Oops, let me draw it correctly. Okay, sorry about the mess. So here is the normal, and this angle is 90 degrees. So this length is 10.36. This length is square root of 10 squared plus 4 squared plus 5 squared. So this one is 10 squared plus 4 squared plus 5 squared minus 10.36 squared. You know what I'm doing, right? This is Pythagoras theorem, and this will tell me it's about 5.774 kilonewtons. You can see it's a lot more normal force than tangential force, parallel force. So it's not likely to fail. I mean, this is all very crude stuff, but I want you to understand how this calculation was done. For surfaces, look for normal directions, which you can obtain by doing cross product. For bars and things like that, you want to look for tangent direction, which is obtained by finding the vectors. Thank you.